All right, so far in this class, we've studied differential equations, and first we looked at first-order differential equations and how to solve those. And we had multiple different methods. We had ways of estimating, and we had ways of graphing those. Then we looked at second-order differential equations, and we looked at solving those with or without kind of a forcing function along with it. So this whole next chapter is going to be about systems of differential equations, and a system of differential equations is more than one differential equation. And so really what this means is that there is more than one dependent variable. And I'll start off with a little bit of a, I guess this is a good example or a good introduction to systems. Okay, so we need to go back though to harmonic oscillators. So let's look at a harmonic oscillator or spring mass system with no external force. So no external force. Let's just give it a mass of 1, I don't know, 1 kilogram, 1 whatever. And then a damping coefficient of 7 and a spring constant of 5. Now I'm going to use y's instead of u's. We've been used to u for the position. I'm going to use the variable y, just because later on it will become a little bit easier to kind of see these. All right, so if I write out the equation for this harmonic oscillator, I'm going to have the mass times the acceleration, so y double prime, plus the spring constant times the velocity, or the first derivative, plus the spring constant times y, all of that equal to 0. And so that's the equations that we've had before for a model of a harmonic oscillator. So what I'm going to do is now convert this to a system. And so what I'm going to do is I'm going to use the fact that the derivative of y with respect to t is equal to velocity. And I'm going to use that fact. So what we've got here is a dependent variable y and a dependent variable v. So I said that there's more than one dependent variable. Y and v are the dependent variables in this case. And we're going to have more than one equation, and the other equation is going to be the derivative of v with respect to t. And that needs to be in terms of y and v. Those are our dependent variables. We want to keep them that way. We don't want anything else. Now remember, so this is kind of some, whoops, sorry, I just dropped my pencil. Remember, and this is some side work here, that the derivative of velocity is equal to acceleration, and acceleration is equal to the second derivative of position, and we have an equation for the second derivative of position up here. We haven't used this guy yet. All we've said is that the derivative of position is equal to velocity. True statement. What I'm going to do is take this equation and use that and solve for that y double prime. So if we look at that equation that's underlined there in red and I solve for y double prime, I would get that it's equal to negative 7y prime minus 5y. Now y is one of our dependent variables, but y prime is not. But we know that we can write y prime, that's the derivative of position, which is velocity. And now I have an equation for the derivative of velocity, dv dt, in terms of v and y. So that equation is going to go right here, minus 5y, and there's our system of differential equations. So that system is a representation, just a different representation, to the exact same equation that we had before. And we'll go through, kind of all of this chapter goes through how to solve these. Now, when we do solve them, The solution also looks a little different. Because we have more than one differential equation, we're going to have more than one part to our solution. So our solution really is going to look like some kind of a representation for a y equals and a v equals. They're both of those things. All right, so let's do another example of convert. So let's convert x times y double prime plus 1 plus x squared y prime plus sine of x y equal to 2. Let's convert this to a first order. Notice that those were both first order differential equations that I had in the last video, to a first order system. And we can do this using the exact same fact that we did before. It's sort of labeling and saying, you know what, we might not have position and velocity here, but we can still say that the derivative of position, or derivative of y, with respect to x in this case, is equal to v. All right, so that's always the first step, and it's always exactly the same. There's no work to be done there, no creativity. It's just that dy dx is equal to v. And then we need to find an equation for dv dx. And we do this by solving for the second derivative of y, the same as before, like saying basically that the derivative of v is going to be acceleration. All right, so to solve for y double, I'm going to do this work on the side. I've got x, y double prime. Maybe I'll bring everything else over to the other side of the equation. So I'll have 2 minus 1 plus x squared y prime plus sine of x times y. Oops, how about a minus in there instead? That's going to be a minus because I wanted to subtract that over to the other side. And then I need to divide by x, so y double prime is going to equal 2 over x minus 1 plus x squared all over x times y prime minus sine of x over x times y, and that is going to be dv dx, whatever y double prime is. 2 over x minus 1 plus x squared over x, except for this time, instead of y prime, we've already determined that y prime is v, minus sine of x over x times y. Right, so there's our system of differential equations. This is one that we're not going to look at solving in this class. We're going to look at solving ones where the dependent variable only has constants out in front and not functions. So these functions out in front of there complicate things, and then we also have this function without a dependent variable. It does not have v or y, and that would require some kind of a method of undetermined coefficients with multiple equations to solve that. All right, now there are some very special systems that we can solve right now. So let me give you an example of this. Let's solve dx dt equals 2x and dy dt equals 3y plus x squared. All right, our dependent variables are x and y in this case. Our independent is t. And what makes this one really so special is the fact that we have one of the equations where the dependent variable is the only variable in it. This equation does not have y, and so as it is already solvable. We know how to do this. We've done it a bunch. I'm not going to go through the exact solving of it, because you guys have done this a lot. Just use separation of variables, and we get that x is equal to c e to the 2t. Now what we're going to do to solve for y is we're going to put that x into that other equation. All right, so then what we get is dy dt equals 3y plus x squared. So that's like a square c, and then e to the 2t squared, that would be e to the 4t. All right, let's see. How would I solve this? I think I'd probably use integrating factor. So let me subtract 3y over to the other side. And then I have to get my integrating factor, which is e to the integral of whatever is out in front of y. So my integrating factor is e to the negative 3t. So I'm going to have multiplying by the integrating factor on both sides. E to the negative 3t equal to c squared e to the t when we combine those. Alright, so on the left-hand side, I'm going to get y prime e to the negative 3t, all of that prime. That's undoing that product rule. Now I can integrate both sides. On the left, I get y e to the negative 3t, and on the right, I get c squared, that's just the constant, integral of e to the t is e to the t, and then I get another constant. We'll call that k. Divide by the integrating factor, which would be the same thing as multiplying by e to the positive 3t. We're going to get c squared e to the 4t plus k e to the 3t. So our solution to this differential equation, we usually put this in a vector form where we've got an x of t on the top of this vector and a y of t on the bottom. The x of t was c e to the 2t, and the y is c squared e to the 4t plus k e to the 3t. All right, so there's our solution, and this is just one very simple example of a solution that we can solve right now with other methods that we know from before. I also just want you to make a note that this c right here in the y equation, I kept as c the whole way through. I didn't change c squared to a different c, and that's because whatever number this is going to kind of keep as that same number throughout this entire solution. So it stays as whatever c is, has to stay as c. Okay, let's do a little bit on some applications. All right. Before, we dealt with tanks with only one tank in them, and we were able to write out a differential equation that represented the amount of, in this example I'm using salt, but the amount of salt in a tank at any time. Now we're going to add another tank, and that means that we're going to add another differential equation. The ideas of the setup here are the same. So let's call this one, right here tank X, or the amount of salt in the tank X, and the amount of salt in the second tank, let's call that Y. So our first differential equation is going to be for the amount of salt in tank X. Now what I'm going to do is sort of ignore that this other tank exists, and I'm going to concentrate only on this left tank here. Now what's going into the tank? The first thing we have going into the tank is this 3 gallons per minute, and it's got 1 pound of salt per gallon. So that means if I multiply those together, I would have 3 pounds of salt per minute going into the tank there. Now going out of the tank, so I'm going to subtract that, and right now I'm focusing on this part right here. So going out of the tank at 4 gallons per minute times some pounds of salt that's in that tank, and then I've got to divide that by the number of gallons in that tank. All right, so let me think about this. I've got 25 gallons. I've got 3 gallons going in. I have another gallon coming in from here, so that's 4 gallons per minute going into this tank, and 4 gallons per minute going out of the tank. So that means that that 25 is just staying as 25. It's not going to change because there's 4 gallons total going in, 4 gallons total going out. All right, now I also, and this is a little bit different from what we've done before, we now have this guy coming in, and that's coming in from this other tank. So that is adding to this tank because it's going into it, 1 gallon per minute of solution that's coming from tank Y, so it has Y amount of salt in that solution, divided by the volume in that tank. Now I have to think about this second tank and the volume in it. It's got 50 gallons, and I have to ask myself if that's changing. So going into the tank is 4 gallons, and exiting is 1 plus 3. So 4 gallons exiting, 4 gallons entering. That volume is not changing, it's staying a constant 50. So there's my differential equation for the amount of salt in that first tank. I'm going to do the same thing for the amount of salt in the second tank. Now, that second tank does not have any kind of pounds per salt entering the tank like the first one did. The only thing that's entering the tank is this guy right here that's coming from the first tank. So entering that tank, so that's a positive because it's entering it, 4 gallons with a concentration coming from that tank X divided by the volume in tank X, which we determined was 25. Now minus, I've got that 1 gallon right here exiting the tank, so that would be 1 times it's coming from that tank Y, so that's 1 times Y there. Whoa, I messed that one up. 1 times Y, okay. And then this one is 1 times Y as well, divided by the volume in that tank Y. And then also exiting tank Y is that 3 gallons per minute with a concentration of Y and a volume from that tank Y of 50. All right, simplifying things here, dx dt is going to equal 3 minus 4/25 x plus 150 y, and dy dt is equal to 4/25x minus 4/50y. I could simplify that fraction a little bit too, but that's okay. Oh, do you know what else I should add is the initial conditions. So not only do we have these, but we also have that x at 0 is, how many pounds of salt are in that first tank? Looks like 5 pounds of salt. And the amount initially of salt in that second tank, y, is, it looks like 12. All right, and there is my initial value problem for a multi-tank setup.